Everybody, and welcome to the 2022 Photonics Spectra Conference. You're joining us right now with Dr. Alex Kenich, who is sales engineer at Alpes Lasers. He joined Alpes Lasers in 2020 after completing his doctoral research at Imperial College London, and he has a background in quantum mechanical simulations and nuclear engineering. This talk is presented by Alpes Lasers, and in it, Dr. Kenich is going to be showing you the latest mid-IR technologies that Alpes Lasers has brought to the market. If you have any questions or comments, you can type those into the conference chat box at any time. And if you missed part of this talk, you can come back later, watch it on demand. So that's all from me for now. I would like to introduce Dr. Alex Kenich. Welcome.
Hello everyone, my name is Alex and I'm a sales engineer at Alpes Lasers. Today I'll be giving you a brief overview of the mid-IR products which we offer. Afterwards, if you'd like to contact me, you can send me an email at sales@alpeslasers.ch. So let's get right into it. Just a brief overview of Alpes. Our tagline is innovating photonics, and we've stayed true to this by being present at several of the breakthroughs in quantum cascade laser technologies over the past 2 decades. One thing we like to mention is that we were the first company to offer quantum cascade lasers on the market, and this was back when we were founded in 1998. Following that, we were also the first to commercialize the first continuous wave laser in 2001, and then the first broad-gain quantum cascade laser in 2009. As I mentioned, we were founded in 1998, and this was done in Neuchâtel in Switzerland. And one of our founders is Jerome Feist, also known as the co-inventor of the quantum cascade laser, Antoine Müller, and Matthias Beck. Diving deeper into our history, in 1994, Professor Jerome Feist co-invented the quantum cascade laser with a team at Bell Labs, and this team included famous names like Federico Capasso and Alfred Zhou. 4 years later, Professor Feist co-founded Alpes Lasers in Neuchâtel. In 2004, we were the first to offer quantum cascade lasers with distributed feedback. This means that these laser devices incorporated a grating directly on the chip, which allowed these lasers to laze in a single mode fashion. In 2006, we began to offer external cavity lasers. These are lasers where you have access to both facets, where they're intended to be used in an external cavity configuration, like the litro configuration. And this way you can utilize optical feedback in order to get higher powers and broad tunability. In 2015, we developed a new kind of distributed feedback laser called the Extended Tuning DFB QCL, or QCET for short. And these incorporate a resistor directly next to the chip, which is powered by a separate current source. And this allows you to achieve the entire tuning range of the chip using only current without having to change the temperature of the laser. In 2015, we launched our high power sources. High power refers to QCL devices with at least an average power of 1 watt and more than 9 watts of peak power when you're using short pulses. Also in 2015, we began to offer the so-called vernier lasers. And these are like the distributed feedback lasers in that they're single mode, but they have a very large tuning range. And these use the vernier effect. In 2016, we began to offer an external cavity laser kit. And the purpose of the laser kit is to be used together with an external cavity laser to form a complete light source. And this way you don't have to get your own driver, you don't have to get your own control electronics and a body for the actual system to reside in. This is a turnkey system, so to speak. In 2019, we achieved an efficiency record, or rather a charge density record, where we had the lowest continuous wave threshold current density for quantum cascade lasers at any wavelength. So if you're familiar with current density, 430 amps per square centimeter in continuous wave at room temperature was the record in 2019. Also in 2019, we began to offer shortwave infrared lasers. And these are laser diodes which utilize the same material substrate as for our quantum cascade lasers. In 2021, we began to offer interband cascade lasers. And these are particularly interesting because they fill that gap between around 3 and 4 microns where there are many applications, particularly in gas spectroscopy of organic compounds. And this brings us to today. I should note that this is a very condensed list of the things that we've been working on. We have a large research team, and we've been publishing prolifically over the past few years. So if you'd like to see more, just search our publication list on our website. Moving on to our laser sources. So this is a nice snapshot of what we offer in the infrared spectrum. So we have in the far infrared our terahertz quantum cascade lasers. Covering most of the mid-infrared are our QCLs, and then bridging the gap between mid-IR and shortwave infrared are our ICLs. And then we have laser diodes moving almost up to the visible spectrum. Specifically, we have infrared laser sources from 0.9 to 16 microns, and the terahertz span from 1.5 to 5 terahertz. We also have a wide variety of laser sources. So these could be either Fabry-Perot devices or single mode devices, or even external cavity lasers and our special QCXT and QCET lasers. One of the most popular applications for mid-IR lasers is clearly gas sensing. And this is because in the mid-infrared, you have many molecules which display strong absorption bands. So, for example, here I'm showing you the spectrum from 3 microns all the way up to 14 microns. And you can see these very strong, almost completely opaque bands for various different gases. And this is great because it allows you to measure the concentration of these gases in cells where they're very, very low concentrations, down to the parts per billion. And this is great because it means that there's little or no need for calibration often. We offer not just laser sources, as I mentioned previously, with DFB lasers, Fabry-Perot lasers, high power and terahertz. We also offer the electronics in order to operate and control these lasers. So we offer drivers, temperature controllers, and various controllers for the external cavity. In terms of assemblies, we can offer things such as laser kits, which make them complete light sources when you combine them with an external cavity laser. We offer pigtailed components if you need something that needs a fiber connection. We also have various different housings which you can use, and these housings can include lenses, they can include Peltier elements, or even just spaces where if you definitely need to purge the environment, let's say with nitrogen, you can do that. There are also custom systems, but these are produced on an as-needed basis. We have a team which is dedicated to producing these custom systems. So again, if you have a particular application, just let me know and we'll see what we can do. In terms of services, we also provide research for hire. We have a very strong team of laser scientists back in Alpes, and we can produce custom laser sources or even custom systems. And now to dive deeper into the distributed feedback or DFB QCLs. Here are some of the key characteristics that we make for our standard offer. All the DFB lasers will have a wavelength somewhere in the range from 4 to 16 microns. Now, we have thousands of these lasers in stock, which we've created over the past 20 years. And so if you need a very specific wavelength, please check with us because chances are we might have it. We do publish a stock list on our website, and that's your first point of call. You can check there, and if you can't find the wavelength that you need on our website, you can send us an email and I'll be able to check if we have something that might not be characterized yet, but which would work for you. In terms of optical power, typically we offer these lasers with powers from 1 to 100 milliwatts. It is possible to get lasers with powers in excess of 100 milliwatts, even in excess of 200 milliwatts, but these are far more rare, and this is because their yield is a lot lower. And this has to do with the fact that not every material is pristine, and various defects can cause parasitic effects which reduce the power. But definitely any power that you request will be considered as a minimum, And then anything we'll offer you will have at least, let's say, 10 milliwatts of power if that's what you need in your specification. All of these lasers are single mode emission. And in this sense, we say that in continuous wave, you will have around 1 megahertz of line width. And this is more than enough for most spectroscopy applications. These are all room temperature operation devices. And by this, what I mean is that you do not need any kind of cryogenic cooling. These will operate at normal 20 degrees, but the temperature of the chip itself may need to be modified using a Peltier element. And this would be included in the housing, and you would have a temperature controller, and as long as you have a heat sink, which is around 20 degrees Celsius, you'll be able to operate all of these lasers. And as I mentioned before, these are compact sources. They're very light. They're the size of your fingernail, let's say. And so depending on how you'd like these packaged, or even if you don't need them packaged, we can accommodate that. Just let me know, and we'll be able to offer them in various different housings or systems as you need them. Moving on to the multimode QCLs. Here are the key characteristics. For the multimode QCLs, we offer them in wavelengths within the range of 4 to 14 microns. And again, we have thousands of these lasers, so if you don't find it in the stock list, please let me know and we'll search for them. The optical powers for the multimode lasers range from 1 milliwatt all the way to 1 watt average power. And as I mentioned previously, 1 watt is considered the base for the high power lasers. That's why we have this HP here. So with these, you can get up to 250 wave numbers in spectral width. So 250 would be the special class of so-called broad gain lasers, because these have been designed to operate over a very large spectral range. But typically with a normal Fabry-Perot laser, you would expect around, let's say, 30 wave numbers of spectral width. Once again, these are all room temperature operation lasers, but they might include a built-in Peltier element in order to modify the temperature. Again, as long as your heatsink is at around 20 degrees Celsius, you'll be able to operate any of these lasers within the range specified in their data sheets. And once again, these are compact and light. The main difference between these and the DFB lasers is that these do not include the grating, and therefore that's why they include high power lasers, because the grating does tend to have a bit of a parasitic effect on power. Now on to exotic QCLs. These include things like frequency combs, the QCET lasers, and the QCXT vernier lasers, which I spoke about earlier. For the frequency combs, our standard offer is at 7.95 and 6.02 microns. And as far as I know, we are the only ones who offer frequency combs at these wavelengths. If you would like frequency combs in a different wavelength, then we'll have to make that a development project where we go through various different iterations to make sure that they have comb operation at that wavelength. It's not a trivial process at all, so that's why we only have this small set of things which we offer for frequency combs. And for QCET lasers, so this is extended tuning, this is a matter of adding a separate resistive element next to the chip. So any DFB that you find in our stock list could potentially become a QCET laser. Just let us know and we'll see if it's possible to do that, if they're a good candidate for turning into a QCET laser. In terms of QCXT lasers, which utilize the vernier effect, these are completely separate devices because you need to have a laser chip which allows this vernier operation in the wavelength range that you need, such that you get single mode operation at various regions when you change the current flowing through a heater next to the side of the laser. So we call them extended tuning or extremely tunable lasers because they have a large piecewise single mode tunability, which means that, let's say, within 100 wave numbers, you'll be able to access around 40 wave numbers in a piecewise manner in different so-called regions. So if you would like an XT laser, or if you would like to see some details of how they've worked, there's a very great paper recently published by one of the research groups in Italy, where they go into detail about how these lasers operate and what kind of performance you can expect out of them. And once again, these are room temperature operation lasers, 20 degrees Celsius on the heatsink, and you're fine. And they're compact and light, and they can be integrated into various different housings and systems. Now moving on to interband cascade lasers. For now, we offer these in wavelengths between 3.2 and 3.6 microns. The standard offer that we have is for broad gain ICLs. So these are multi-mode devices which have powers up to 10 milliwatts. But we also do have some material, not that much, but we have some material which is single mode. So these are distributed feedback ICLs. But this is not something that we expect to turn into a standard offer because it's a more difficult process to develop single mode ICLs. And if you would like these, it would have to be a development project specifically for your chosen wavelength. For now, we can offer these with 8-week lead times. And we offer these in different packagings. If you need a TO3 housing or HHL housing, this is what we can offer for your ICLs. Now, moving on to the external cavity lasers. Over here, you can see some of the submounts that we use for the external cavity lasers. And these submounts give you access to both facets of the laser. And this is necessary because you need to perform optical feedback with these lasers in order to use them in an external cavity. Now, here I show you a drawing of the external cavity box that we use. And this will include all the internals, including the Peltier element, the control system, the diffraction grating, and various ports in case you want to perform things like purging of the internal system. So sometimes a client would like to purge with nitrogen in order to drop them down to very low temperatures and not have to worry about condensation, things like that. More specifically, to show you what's inside the external cavity kit, you have the heatsink upon which the laser chip will sit. And this will be connected to various peripherals outside the box. So inside the box, you have the heatsink, a pulsar, which is there to provide the pulse to the chip, and the rotational stage where you can choose the wavelength that you want to output from the laser beam. There's also a water cooling connection or a dry air connection if you want to purge the internal environment. And on the outside, we would offer things like the servo driver, which is connected to a power source, a Raspberry Pi, which is also a control interface, which will have to be connected to a separate power source, and a temperature controller, which is connected to the Peltier element, which is in the heatsink. And down here, I'm showing you two different plots of some of our broad gain lasers in an external cavity configuration. On the bottom left here, we have a broad gain interband cascade laser emitting from 3.2 to 3.6 microns. And you can see here the average output power that you can expect at each wave number. And on the bottom right, for the other end of the mid-IR, we have a broad gain laser from 10.8 microns to 13.7 microns. And this shows you the typical spectrum that we can expect when we have this in an external cavity configuration. Notice, by the way, that the interband cascade laser operates in continuous wave within the external cavity, whereas all our quantum cascade lasers are required to operate at lower duty cycles. Here we show a 5% duty cycle, because quantum cascade lasers generate more heat during their operation. They're typically less efficient in that sense than interband cascade lasers. And as for our terahertz quantum cascade lasers, these are a special case where all of them require cryogenic cooling. So we're talking very low temperatures below 200 degrees Celsius. Typically, we'd offer these lasers with a Dewar So here's an example of one of these nitrogen dewars, liquid nitrogen dewars, which have a little window in order for the beam to pass through. If you're going to be using liquid nitrogen, we're talking 77 Kelvin. So at this point, we have to start using Kelvin rather than Celsius. But they can also be operated with liquid helium, far lower, closer to around 2 Kelvin. And the lower temperature you use typically means that you'll be able to extract higher power from these lasers. And you can achieve up to 5 milliwatts of average power, which for a terahertz laser is actually very high. Typically, you'll see terahertz lasers offered with powers in microwatts. So maybe the 10 or 100 microwatts. But we can go up to the milliwatt range. Once again, these can be operated only in pulsed mode, because if you're going to be operating them for longer duty cycles, there's more thermal dissipation, and therefore they won't emit, or perhaps they won't even laze in the terahertz region anymore. So these have to be operated in very low duty cycles. Currently, our terahertz material is provided by a special lab at ETH Zurich. And so our availability of terahertz laser chips will depend specifically on what's being developed over at ETH. So once again, you'll have to contact us, and it needs to be done on a case-by-case basis. Sometimes we'll have material for certain wavelengths and not others. And so we'll need to know very specifically what you need and when you need it by. Typically, we're talking around 10-week lead times for these lasers. Moving on to our different laser packaging options. So depending on your application or your technical requirements, you may need a packaging or even no packaging for your laser device. And this can include anything from a packaging with a collimation lens, thermoelectric cooler, fiber coupling, or maybe just a very compact housing, again, depending on the specifics of your application. So moving on to the specific mountings and packagings that we can offer, I'll work my way up from the most simple packagings and work up to the more complex housings. So the simplest thing we can offer is the laser as a bare chip. And this would be provided in a gel pack, as shown here, and only tested in pulsed mode because of thermal limitations. This is, however, the ideal form if you need a very large volume of lasers. So for example, you can easily have more than 100 chips on a single gel pack. The next step up is to move the chips and mount them onto an aluminum nitride submount. This vastly improves the heat transfer, and this allows us to test it in both pulsed and continuous wave mode. So in addition to allowing this improved heat transfer, this allows easy product integration. So there are pads for you in order to do wire bonding here as necessary, and it's a very small footprint on the aluminum nitride mount, and this works very well for most applications. I think this is one of our most popular submounts for very large volume orders. And then the next most popular form is to have this aluminum nitride submount with a laser on it itself mounted on a copper submount. Again, it's copper because it improves the thermal conductivity, and this includes screw mounts. So again, making it easier to integrate it into a product, in this case, using screws for fastening. And there are many different kinds of submounts depending on what you need in your application. So for instance, the submount I show here, you only have access to the front facet of the laser, but we do have submounts where you have access to both facets of the laser. So for example, in the external cavity laser submount, you have access to the front and the back laser in order to perform optical feedback. The next step up for mounting is to package the laser. Now, these are our most common housing options. The first of which is the TO3 can. So in the TO3 can, we can offer the laser together with a thermoelectric cooler and a collimation lens. But in this case, you can only get up to 3 watts of thermal dissipation. And this is a limitation of the geometry. Here are some of the dimensions here. It's important to note that for the shortwave infrared diodes, we use a TO6 can instead. And this is because we find that this works better for those particular lasers. The next step up is to use our high heat load or HHL packaging. And once again, you can have a thermoelectric cooler and a collimation lens in this packaging, but this time up to 15 watts of thermal dissipation. It is a slightly larger footprint, but depending on the laser, sometimes it's the only possible packaging that we can use simply because we need the extra thermal dissipation. In addition, we have a heatsink with water cooling available specifically for these HHL packages. Another popular option, which is typically used by scientific laboratories and universities, is the laboratory laser housing. Now, this only includes a thermoelectric cooler. So we don't have a collimation lens in here. Rather, we only have a window. But the advantage is that it's not hermetically sealed. So if necessary, you can remove the top and you can replace a laser chip. Again, it's a much larger housing, but if you have multiple laser chips, sometimes this might be worth it. The only problem is that in this case, you would have to do a realignment of the laser if you're collimating the beam every single time you decide to change it. And that can be a bit of a difficult process. It has a built-in water cooling circuit, so you can see the water cooling connectors here. And now to close with the services which we can provide. As I mentioned before, we have a large R&D team and we have engineers on site with a laboratory and a workshop, so we can do everything from the component design all the way to the custom fabrication and integration of tools. Now, we split these into 4 different areas. So component design, where we design but not necessarily create the sources. Contractual R&D, this is typically what we do with small to medium enterprises, exploring new kinds of products or applications. And then there's fabrication and integration, where we create custom fabrications based on maybe your designs or maybe our designs if we also do the components there. And finally, integrations, where if you have some components which you wish to integrate, but maybe you don't have the expertise, we'll provide that service. And finally, here I just wanted to show you a very condensed list of some of the companies which we've worked with. As you can see, they span many different industries, over many different countries, and many different kinds of applications. And over the past 20 years, we've sold several thousands of devices, many different kinds, to all of these clients. And hopefully we can add you to this list soon. And with that, I'd like to close. Thank you very much for listening up to this point. If you'd like to get in contact with us, please send an email to sales@alpeslasers.ch and visit our website at alpeslasers.ch and follow us on LinkedIn if you can. Thanks again, and goodbye.
Thank you so much. And thank you everyone in the audience for your attention. And thanks for your questions and comments. If you haven't already, you can type those into the chat box. And thank you for joining us for overview of mid-IR products at Alpes Lasers. This talk is presented by Alpes Lasers and is part of the Photonics Spectra conference, which is hosted by us at Photonics Media. And you've just heard from Dr. Alex Kenich of Alpes Lasers. Thank you so much.